For the video. Trying the music again. You're gonna have to let me know how it sounds, right? This one chemistry survival tip of the day: wear a hat. Anyway, we're gonna be talking about heating curves again, and make sure you realize slanty parts are changing temperature, flat parts are changing state. So now we gotta quantify it. We're gonna quantify it by finding the quantity heat, and heat is gonna be Q. Q is gonna be calories. Q is gonna be joules. Q is heat. So when I say what's the heat, please give me an answer in joules or calories. Okay. So there's 5 things going on here, but in these 3 sections, the heat is being used to change the temperature of the substance and give it more kinetic energy. So if we want to know how to find the heat during a single state of matter, we're going to need to know the mass of the state of matter, mass of the substance. So mass, symbol M, measured in grams. Okay. We also are going to need to know how much does that temperature change. So temperature change is a final temperature minus an initial temperature, or a delta T. You could also use capital, and it's the change in temperature, so it's going to be in degrees Celsius. Then every substance is going to change temperature by different amounts because of what it's made of. So it's called the specific heat capacity is what we use. It's given the symbol C. It's what we use to compare different substances and how much they change temperature when you add heat to them. So the mathematical formula you have to know is Q heat equals mass times specific heat times delta T, sometimes called Q equals MC delta T. This is a mathematical formula you should memorize. You should know what each part stands for. You should be able to solve for any one of these 4 things. Okay, so let's describe what specific heat means again. Specific heat has the symbol C. Its definition is the energy needed to change 1 gram of a substance 1 degree Celsius. So let's think what that means. When you are standing barefoot in the summer, would you rather be standing on the cement or on the grass? Well, the substance that changes temperature more quickly lets heat pass through it more quickly, and so has a low specific heat. So cement has a low specific heat, between the heat goes into you. Grass has a higher specific heat. Oven and an oven rack. Okay, so if you put your hand in this oven, would you want to grab that metal part, or would you just want to keep your hand there if you had to? Probably neither, right? But grabbing the metal, because metal has a low specific heat, the heat would transfer right into you because the metal has a low specific heat. But the air in the oven has a higher specific heat, and so it would transfer heat more slowly. High specific heat means transfer heat slowly. I want you to think about water and sand, and which one you think has a high specific heat and a low. All right, so where do we get this information? Specific heat is these 3 columns on this data table, or these 3 columns on that data table. What's the diff? Calories, joules. But notice the units. There's calories, there's grams, and there's degrees Celsius. So you need to know all 3 of those things to compare substances. So water has a specific heat of 1 calorie per gram degree Celsius, and copper has a specific heat of 0.1 calorie per gram degree Celsius. So which one holds the heat? Water holds the heat more. Copper transfers it quickly. So copper will change temperature 10 times as much as water does per gram per degree Celsius. Okay? And then here in joules, you can see water still has a pretty high specific heat because these are actually the same values, just different units. Okay, this is like feet and inches. This is calorie per gram degree Celsius, joule per gram degree Celsius. Please remember that 1 calorie is equal to 4.184 or 18 joules. Okay. So now we've quantified along these lines, saying that Q equals MC delta T. But what about the heat added during the potential energy changes? Well, can we use Q equals MC delta T? Well, no, because there's no change in temperature. It's a flat line. So initial temperature is the same as the final. Delta T equals 0. So this equation becomes nothing, right? So in order to figure out the heat during a phase change, we're going to need to know the mass again in grams, and then symbol G. And we're going to need to know the energy of a phase change. The symbol we use for the energy of a phase change is called delta H. This time it doesn't mean you have to subtract anything. This is just what it's called. Okay, the enthalpy of the phase change, heat of the phase change. And the units for that are going to be calories per gram or joules per gram. So you need to know these 2 things to find Q. need to know, so the formula for this, the heat during a phase change is equal to the mass of the substance times the heat of that phase change. So make sure you memorize that formula in each part of it, okay, so that you can solve for any missing part. All right, so a little more information about the heat of a phase change. Heat of fusion is when you add 1 gram, how much heat it takes when to melt or freeze 1 gram of the substance. So if you're melting it, it's fusion. If it's freezing, it's solidification. But it's going to be the same amount of heat, just adding it in or taking it out to change 1 gram of the substance into a new phase. So the units are going to be heat per gram, or heat per mole. All right. So if you're doing this phase change, it's on the low part of the heating curve, and it's going to be solid to liquid. If you're adding the heat in, liquid to solid. If you're taking the heat out. This is the formula for it. Vaporization. Anytime you see vape, you should think gas. Right? So this phase change is a gas-liquid phase change. So the energy it takes when 1 gram of the substance either boils or condenses, it's called the heat of vaporization or the heat of condensation. So this is the phase change of a liquid to a gas, that's vaporizing, gas back to liquid, is condensing. Okay, so vape, condense. But guess what? They're going to be both the same value just depending if you're adding the heat or taking it away. So the units again, calorie per gram, joule per gram, or kilocalorie per mole. And here's the equation. So let's see where we find this on our data table. The 7 and 8 is delta H vape, condense. Columns 5 and 6 on your data table are delta H fusion or solidification. And on here, on the other side of your data table, it's just the delta H vape, but that's in joules, and this is delta H vape fusion, and that's in joules. Okay, so each part of a graph gets a calc, so before you can figure out the heat, you gotta have the graph. So what you do when you see a graph is you put the temperature 0 degrees Celsius, other temperature is 25 degrees Celsius. I have to include those. And then I look to see what my substance is. Okay, this is ice. So I'm talking about H2O. So does H2O have any significant things? Well, 0 is a melting point. 25 degrees is below the boiling point. So we have one phase change because ice has to turn to liquid, solid to liquid. And then we have one temperature change as the liquid warms. So we have to do a Q equation for this part of the graph. Q is going to be equal to the M delta H of fusion for that part of the graph. Plus, we have to add the Q. Oops, I don't need to put the Q there, so I'm just going to put this part of the graph as a Q of MC delta T. So now, if I want the total heat for this whole thing, how much heat Q total, I have to add those two together. So I would take this Q, I would get the mass. It says 20 grams given in the problem. Delta H of fusion is 334.7 joules per every gram. Plus the mass again, still 20 grams. Okay, we haven't changed the mass. Specific heat is 4.18 joule per gram degree Celsius. And then we have to figure out the delta T. So delta T, take the final temperature 25 degrees minus the initial temperature of 0, and you get 25 degrees Celsius for delta T. So then I could plug that in there, 25 degrees Celsius. So then this gives me 6,694 joules, because grams gets a gram, plus multiply that together, you get 2,090, and grams cancel grams, Celsius cancel Celsius, so we're left with joules, and then you add them up and you get 8,748, 8,784 joules total, okay? All right, okay, hey, how much heat? Look for Q. So we're going to need a graph. So on my graph, I'm going to put -6 degrees Celsius and 116 degrees Celsius. But wait, this substance is H2O, right? So I need to go from here to here, but there are two very important temperatures in between this range that I have to consider, the melting point and the boiling point. So I have to take, it's going to be solid until it reaches 0. When it melts, solid turns to liquid. And then it's going to be liquid to 100, and then it's going to boil, and then it's going to be gas to 116. So there are 5 sections of this graph. So I'm going to have to get total heat. I'm going to have to add Q1 plus Q2, 3, 4, and 5. All right. So what kind of Q would I use here? Q is going to be equal to MC delta T. So I have to plug in the mass. And this time the mass is 5 grams. Specific heat. Now since this says solid, I use specific heat of solid. That's ice. That's 0.5 calorie per gram degree Celsius. Okay. And then this says delta T. So the change in temperature is 0 minus -6. So I have 6 degree temperature change, right? So I got to put 6 degree temperature change. Then I have to get a Q for this part of the graph. This is a phase change, so Q is going to be equal to M delta H. Which kind of delta H? The solid liquid phase change is fusion. So I have to do the 5 grams of the substance times the 80 calories for every gram. I know I'm on the right track because those are going to cancel. Okay. This Q is another temperature change. So Q equals MC delta T here. The mass is still 5 grams. We haven't changed the mass. The specific heat now has to be heat of liquid. So I have to put 1 calorie for every 20 degrees Celsius. And then I need a temperature change. So I have to do 100 minus 0, 100 degree temperature change. Okay, look, Celsius cancels Celsius, grams cancel grams, and I'm left with the Q, calories. Liquid to gas phase change is a phase change. So we'll use a phase change equation. This time it's vaporization because there's a gas involved. 5 grams times the heat of the vaporization is 540 calories. Every time a gram vaporizes 1. Alright, finally this part of the graph is going to be another Q equals MC delta T. Alright, so I'm going to need 5 grams of my substance. The specific heat of the gas is 0.5 calorie per gram degree Celsius. And the temperature change is 116 minus 100 equals 16 degrees Celsius. So I have to plug that in, 16 degrees Celsius. So then I have to add Q for the solid plus Q for the solid to liquid phase change plus Q for the liquid plus Q for the liquid to gas phase change plus Q for the gas. All of these answers together to get the total. Alright, so if you look at your data table, you'll notice for every substance that the vaporization phase change heat is always bigger than the fusion phase change heat. But why? Let's talk about forces. So in order to get something to go from solid to liquid, you got to take this and give these guys a little more potential energy, breaking the bonds between them so they can flow around. But we still have attractions in liquid. And so these molecules don't build up too much potential, just a little more potential. So the delta H of fusion is small compared to breaking these bonds completely. Look at the potential change in here. These are so much farther apart, it's a higher potential. So the delta H of vaporization is going to be big compared to the fusion. All right, we're on the review part, so make sure you know your fuses from your vapes. Math is fun. Yeah! Alright, the heat curves tells you the equations. Use M cap for slanty, M delta H for flatline. Each segment gets its own calc. You add them together for total heat. Use your heat data table to get some of your numbers. Solve for missing pieces and read chapter 17 and 13. Peace out. After you look at the video, at the objectives. Really, peace out.